So welcome back everyone to the Strength Seminar series. For the first talk of today, we have David Prieto from Utrecht, who will tell us about the complexity of effective theories in the landscape. Please take it away.
Well, hello, everyone. First of all, let me thank the organizers for giving me the opportunity to speak here today. In this talk, I want to present some of the recent results that we have had in collaboration with Thomas Green, his PhD student, Mick Van Vliet, and two former master students, Martín Carrascal and Ferdi Ellen. And the topic will be to try to apply some recent developments on mathematic model theory, more specifically on minimality and sharp minimality, to quantify the complexity of effective theories and try to see what implications this has on the swampland program. So let's start. Let me start with opening with some more philosophical question. That's what's the language of nature? And in theoretical physics, we always think that the answer is mathematics, but mathematics can be very wild in general, and we don't expect every mathematical abstraction to be realized in nature. So it would be nice to find an optimal mathematical framework that can cover all features that can be found in nature, but that does not include what we could call physically ill-defined objects. So how can we start to look for this optimal mathematical framework? Well, when we try to push our mathematical models to the limits in physical theories, we usually can arrive to pathological behaviors that are signaled by infinities popping up in the theories. So some kind of finiteness condition should be a good starting point. And more explicitly, we will focus on conditions about finiteness of information. This can sound fairly reasonable, but in the language we will develop, we will see that generic quantum field theories, for instance, will not naturally have a finite complexity description. But once we try to make contact with quantum gravity, we know from the swampland program that things become much more constrained. There are a lot of additional properties that quantum field theories need to satisfy in order to be compatible with quantum gravity. And for example, the no global symmetries conjecture or the distance conjecture are deeply rooted in finiteness properties, like finiteness of entropy, finite number of black hole remnants, or the possibility of only moving up to finite distance in modular space. So all of these ideas seem to be extremely connected with seem to hint at the fact that the quantum gravity is rooted in notions of finiteness. So what we want is to formalize this idea and unify the different swampland conditions about EFT statements into a coherent and solid framework about logical and geometrical complexity. And we will find this framework in what we call tame geometry, which is a mathematical formalism that has been developed over the last 20 years, and more specifically, a subfamily of this tame geometry that's called sharp minimality, which is very recent and has been developed in the last 5 years. And the idea will be to quantify objects and assign them a complexity in terms of two integers that we call the format f and the degree d. And we will try to use this to quantify the complexity of effective theories. And those that do not accept this characterization for finite format and degree, then we will say they belong to the swampland. So that's the idea of the talk. It will be structured in this way. I will start presenting the formalism of tameness from a mathematical point of view. Then we will apply it to effective field theories in generality. We will illustrate it in an example without gravity in Seiberg-Witten, and then we will connect with gravity and discuss some possible implications for the swampland program. So let's start. The main idea, the main goal of tameness and non-minimality is to generalize notions about finiteness to continuous sets in a way that it's consistent with logical formalism. So the core object for tameness and non-minimality is the tameness structure, which is a collection of subsets of Rn that satisfies the following three properties. Any subset of Rn in this structure must have a finite number of connected components. This is where the finiteness comes into the theory. It must any structure must contain the collection of the zero sets of polynomials, and it must be closed under set theoretical operations. And this gives them the formal logical structure of the object. And we can apply this directly to functions by considering them as graphs, the subsets of Rn, and see we can put them inside inside any given tameness structure. And it's possible to find plenty of examples in this way. We can find polynomials, exponentials, and analytic functions in bounded domains. All of these are tame functions. But it is also very easy to find counterexamples. Anything with an infinitely discrete property, like the sine function with its infinite maxima and minima or an infinite spiral, these are all non-tame functions. So we can think of tame functions as objects which have a finite topological and geometrical information. But how can we quantify the amount of information that we need to describe these objects? Well, this in general, it's not possible for generical or minimal structures. But for a subset of the structures that we call sharply or minimal, this is indeed possible. And that's the idea behind the recent results by Benjamini and collaborators, that they are able to quantify the information contained in a set in terms of these two integers, the format and the degree. And they provide a measure of the complexity in the sense that there is in sharp or minimal structures, there exists a universal function that bounds the number of connected components in terms of the format and the degree for any set in the structure. So if we have a set of format F and degree D, then in the number of connected components of this set is bounded by this universal function, which is polynomial on the degree and exponential in the format. So we have this nice filtration over all the different sets in the structure. And this filtration needs to be consistent with all the set theoretical operations as well. Sharp or minimality is much more constraining than normal or minimality. And for example, the polynomials and the exponentials are still sharply or minimal, but generic analytical functions in bounded domains are no longer sharply or minimal. So let's illustrate how this works in some examples, starting with the polynomials. The amount of information that we need to identify to characterize a polynomial is very straightforward. It's just the number of coefficients. And this is bounded by the number of variables and the degree. So that's just precisely our format and our degree. And with these two numbers, we can bound a lot of properties of the object, like the number of zeros, the minima, the maxima, but also more geometrical oriented properties like the number of data points that we need to approximate the graph of the figure up to a certain error. This is very simple for polynomials, but the power of sharp or minimality is that we can generalize it to other functions. We have said that analytical functions in general are not sharply or minimal. And to see this, we can think of a Taylor expansion and think that we need to specify an infinite number of coefficients. But in many cases, analytical functions like the exponential will satisfy a differential equation that will give rise to a recursive relation between the different coefficients in the Taylor expansion. And at the end, we only need to specify a finite number of them to generate them all. So that's the idea behind one of the main sharply or minimal structures. That's the Pfaffian functions that combine polynomials and differential equations. So we can construct a Pfaffian function by defining a chain of differential equations over the polynomials in a triangular way, in the sense that the solution of the first equation can enter as an argument of the second one, and so on. And then there is a clear, again, assignment of format and degree. The format will be the number of variables plus the number of differential equations required to define the function, and the degree, the sum of the degrees of all the polynomials involved on the construction. So in this way, we see that the format and the degree nicely characterize the amount of informations and the amount of steps that we need to take in order to construct a given object. So this is the general framework that we are going to use. And let's see how we can apply it to characterize the complexity of effective field theories. Well, there are different ways in which one will address this problem. But for this talk, I will focus on identifying the complexity of effective field theory with the complexity of its Lagrangian. And let's start by considering a general effective field theory Lagrangian given by this expression. So it's a sum of local operators, Wilson coefficients, and powers of the cutoff. And we immediately see that this is a challenge to characterize its complexity because we need to take an infinite sum over all consistent local operators. And we also have to consider the dependence with the space of parameters given by the Wilson coefficients that can also be an infinitely dimensional space. So we have a lot of, of degrees of freedom to consider that in principle will lead to infinite complexity for generic effective field theories. But for some subspaces of the parameter space, for particular choices of the Wilson coefficients, there could happen that this sum can be resummed into a function which is tame, for example, a Pfaffian function, and it's what we call the emergence of simplicity. So for some slices of the parameter space, what we call EFT domains, we can have the representations of the Lagrangian with finite complexity. To see how the complexity can change as we move across parameter space, let's consider a very simple family, a zero-dimensional Lagrangian with a quartic potential. And here we have this Lagrangian over n fields. Everything is polynomial, so it's very easy to assign a format and degree to this theory. The format is the number of variables, that's the number of fields, n, and the degree is the degree of the polynomial, 4. But as we move to parameter space, in some limits, this complexity can change. For example, if we take the coupling constant of the quartic potential to be equal to 0, then the degree can drop to 2, just the mass term. And if we take a slice in which two of the masses are equal, we can take a change of coordinates that reduces the degrees of freedom by 1, dropping by 1 the format. So we see that in this simple example, moving across parameter space already changes the complexity. But of course, in more generical cases, we might not have a global description of the Lagrangian valid across the full parameter space that we want to consider. So the approach we will take is to decompose the parameter space into different regions, which would call the EFT domains, and try to construct a description of finite complexity across each domain, and then recover a covering that, by taking the union, covers the full parameter space. In general, again, in a genetic theory, there won't be a EFT covering of finite complexity, but we expect that once we make contact with quantum gravity, this will be the case. We will be able to find finite amount of EFT domains in which one will characterize the theory with finite complexity. And in the case of string theory, for example, these parameters will be most of the time described by the vacuum expectation value of moduli coming from the different, for example, Kähler and compressed structure moduli of string compactifications. So let's now illustrate how one introduce all this formalism into explicitly in a theory, first without gravity, and consider Seiberg-Witten theory. So this is an n equals to supersymmetry theory with SU2 gauge theory in 4 dimensions, and the Lagrangian is given by this long expression, which everything can be written in terms of the derivatives of the prepotential. In this case, we have a moduli space spawned only by one parameter, that's A, the scalar component of one of the chiral hypermultiplets. And if we take derivatives of the prepotential with respect to this modulus, we can construct the gauge coupling function of the theory, which is given by this. At the classical level, it's just a constant, but once we take into account all the quantum correction, it starts to get a series of infinite terms that need to be added. So the question is the prepotential and the gauge coupling constant, do this infinite sum converge to something tame? Well, starting first with the convergence, it's easy to see that the prepotential does converge for large values of A. And if we want to consider other regions, we can also take the redefinition of the variables and take a dual variable given by this derivative, define a new prepotential, and see that this converges also for small values of the new parameter. And this is the famous electric-magnetic duality of Seiberg-Witten theory. Going with a bit more generality, one of the bigger realizations of Seiberg and Witten was to see that the full moduli space of this theory could be identified with the moduli space of a family of elliptic curves given by the zero locus of this equation over P2, where Z now parameterize the complex structure of the elliptic curves. Then one can rewrite both the electric and the magnetic coordinates in the Seiberg-Witten theory in terms of this set. Whenever we have an elliptic curve, then we can take the period map. And this is obtained by computing the periods by integrating the holomorphic form on the elliptic curves over a basis of cycles and taking the quotient. And it turns out that this period map is precisely the gauge coupling constant of the Seiberg-Witten theory. So we have a map between these two objects. On the left-hand side, we have the moduli space of the elliptic curves. It's the 3-puncture sphere, where the 3 singularities are like the 3 degeneration points of the equation of the locus. And the period map takes us to the fundamental domain over the upper half plane of quotiented by this group that it's a subgroup of SL2Z. So this is the period map. It's the coupling function of Seiberg-Witten theory, and it plays a very important role in the full complexity of the Lagrangian of the theory. So we wish to compute this complexity. And how can we do this? So to do this, the idea is to proceed in 3 steps. We cut the modular space in smaller subsets, and in these subsets, we consider the periods, which will be described in terms of something that we call log-Noetherian functions, and whose format can be computed. And then we combine the format of the different pieces into a final result. So the cells we consider are given by disks, puncture disks, and annulus, so pretty simple objects. And over them, we define the log-Noetherian chain, that it's a generalization of the Fabian chain I discussed before, or differential equations over polynomials, but we remove the triangularity condition, and we allow for log singularities and log derivatives of this form, whenever we have a puncture disk or an annulus. It has been proven that periods given by solutions of Picard-Fuchs equations can be written always in terms of log-Noetherian chains, and log-Noetherian chains are tame, and conjecture to be sharply minimal. There is active work by the mathematicians on this topic. They are strongly believe that log-Noetherian functions are sharply minimal. There is already a effective format that gives a bound on the amount of information that you need to compute it. It was developed by Bigiamini 2 years ago, but the explicit split between format and degree is not yet known. But for us, this effective format is good enough to characterize the complexity of the system, and it's given by this sort of lengthy formula. And the idea will be to choose the problem becomes an optimization problem of determining the number of cells and the radii that minimize the final format of the period map. So that's the idea. We have this covering of the modular space of the elliptic curve, and this with these cells and their image under the period map. So we start, for example, with a cell around the electric singularity. We take its image and compute its format using the log-Noetherian chain. We then compute another cell, the complexity of the period map around the magnetic singularity, then around the ionic singularity. And finally, we need another 3 cells around regular points to cover the remaining of the modular space. Put everything together, and we find a format of 54. The number itself, it's not very important. It's just a proof of concept, but it could be useful later on if we want to compare with formats of other theories or other elliptic curves. The main takeaways is that we need at least 6 fundamental domains to cover the full modular space of Seiberg-Witten theory. The main complexity comes from the behavior of the periods around the singular points. And we actually need to have the different 6 cells with 6 different effective field theory descriptions in order to keep the complexity finite. If one were to try to expand the description of one cell to reach one of the other singularities, the complexity will blow up. So in this case, it's crucial to have these different effective field theory descriptions, which are actually the realization of the electromagnetic duality in Seiberg-Witten theory. So these dualities are a way to keep the complexity of the full theory constant. So finite. So that's the idea of this model, and now we will try to see how this can be connected with the ideas from finiteness in quantum gravity and the swampland program. Any questions until now? Okay. Well, then let's continue with the swampland connection, and we have the following proposal to summarize the different ideas about finiteness that are floating around. We define this object MQG lambda that it's a set of d-dimensional effective field theories with a cutoff valid at least lambda that are consistent with quantum gravity. And then we conjecture that this set is definable in a sharply minimal structure with finite complexity, that it's a function of the form of the cutoff that has been chosen. And second, we conjecture that there is a global bound such that any the effective field theory in this set admits a Lagrangian description, which has a complexity bounded by by these two numbers, by this global bound across the set. This is a refinement of the tameness conjecture proposed by Thomas already 5 years ago, because we are upgrading the statement from just tameness and non-minimality to sharp minimality, making claims about quantification of complexity and connection with the cutoff, explicit connection with the cutoff of the theory. The first point formalizes the idea that there are finitely many distinct effective field theories consistent with quantum gravity once we identify the different connected components of moduli spaces as a single effective field theory. And the second point, it's supported by the recent finiteness results regarding the light spectrum of supergravity theories for high dimensions that we expect that will still hold for lower dimensions, but this is still work in progress in the community. And if we combine both statements, this will mean that this space of the model of quantum gravity effective theory is compatible with quantum gravity, will admit a finite EFT covering of finite complexity, and as consequences will be the finiteness, for example, of Calabi-Yau compactifications and the finiteness of flux-Bagua. So it's a very strong conjecture that will be pretty hard to prove, but we can test it in a small scale by looking at the slices of this huge moduli space. For example, we can consider compactifications in particular constructions, like moduli spaces of high supersymmetric settings, given by arithmetic quotients. For example, type 2b in 10 dimension is one of these cases, and this has been proven to be definable in sharply minimal structures, so it satisfies our conjecture. And if we move a step further and consider complex structure moduli spaces of Calabi-Yau manifolds, these are tame as well. These are given by the period maps, which, as we were discussing, are tame, and also have our conjecture to be sharply minimal, and already have this effective description of the format that gives already a quantifiable measure of their complexity.
David, you have less than 5 minutes, let's say.
Okay, I'm finished. Yeah. Okay, thanks. And to wrap, to finish, well, I'm discussing about how to assign complexity to this huge moduli space. This is a very daunting task. This will be a crazy space with a lot of very weird metric, a lot of different connected components across very many different dimensions as well. But our proposal, at least to consider slices of this moduli space, will be to take a time-isometric embedding into Euclidean space in order to measure its complexity. It turns out that we can do this in some examples, and time geometry has a lot of things to say about the properties of moduli spaces, and in particular, properties about its volume growth in terms of the complexity of the objects. So for example, we have this theorem about time geometry that if we have a time set and a time L-dimensional set in Euclidean space, and we take its intersection with an Euclidean ball, then its volume grows at most Euclidean as a polynomial on the dimension L, and with the coefficient being bounded by being a function of the complexity of the time set. The idea being that if we have this object intersecting with a ball, then it can wiggle at most a finite number of times if it's tame, and so the volume can grow only as Euclidean volume. And the number of wiggles will be a function of the complexity. So this is how we recover this bound. And if we assume that the modular space admits this embedding, this time-isometric embedding into Euclidean space, we can apply the theorem and recover the compactifiability condition that was proposed in this paper as a property of modular spaces of quantum gravity theories, which in turn were very strongly connected, this property, with the existence of dualities in quantum gravity. For example, in type 2b, the existence of the SL to Z duality was crucial to recover the compactifiability condition about the growth of modular spaces. And from the point of view of the time isometric embedding, we saw that H, the upper half plane with the hyperbolic metric, does not admit a time isometric embedding. But for instance, if we quotient with the duality group, it does admit a time isometric embedding with finite complexity. So as we see again, this minimal framework has a perfect, well, it's a very nice tool to to characterize the existence of dualities in quantum gravity theories and also in quantum gravity theories. So with this, I reached the end of my talk. I hope I have convinced you that sharp minimality is a good candidate as a language to characterize nature. We have seen that it can be used to measure and bound the logical complexity of effective theories, and we conjecture that those that are compatible with quantum gravity must have a bounded geometrical complexity in this setting. And with this, we can understand some line features like the finiteness of the string landscape, volume growth of modular spaces, and more importantly, maybe dualities, which can be detected as rising when the complexity is going to blow up as a requirement for alternative representations. But there are still many open questions, like how to address the complexity of integral lattices of arbitrary size. Still the problem of the format and degree splitting for the periods. It would also be nice to consider a tame Nash embedding theorem for modular spaces. This will provide a lot of information for the geometrical constraints of modular spaces compatible with quantum gravity if our proposal were to be true. And this will also provide information about infinite distance limits and possible connections with the distance conjecture. And with this, I reach the end of my talk. Thank you very much.
Thank you very much for a very nice talk. Are there any questions? Well, if not, let me begin. Well, you said this already a bit, and maybe it's a bit vague, but could you say something more about the connection to dualities? And if you could use this to predict new dualities, for example, or
Well, yes, the idea is that the connection with dualities is that whenever we expect that there is an infinite complexity arising in a given effective field theory, we should expect to have, at least in the context of quantum gravity and the swampland, another effective field theory or another description in this other region of modular space that admits a new description with finite complexity. And that's what we see, for example, in Seiberg-Witten, which we expect it to be able to couple with quantum gravity. We have these different regions of finite complexity, and regarding the modular space itself, yeah, we have that for the case of the type 2B example, we do require to have the dualities to be able to characterize the complexity of the modular space itself as a finite thing. So more than predict, it can sort of detect when it can distinguish between theories that you will accept or not to be compatible with quantum gravity, I will say. Yeah.
okay, thanks. And I guess this is what you mean, or the connection to the distance conjecture, and this is what you're referring to.
For the connection with the distance conjecture, this is very speculative, but maybe if one went a tame version of the Nash embedding theorem, this will, and we were to believe this tame isometric embedding, this will be giving you some constraints on the kind of infinite distance limits that you could have in modular spaces. So I guess that you could try to connect with the distance conjecture this way, but I don't know how to do it at this point. Yeah.
Thanks. Nacho, you have a question?
Yeah, I do. Thanks, David, for your question, for your presentation. So I have a very silly question, which is from at least the example that you showed us with like Seiberg-Witten. It seems that most of like the complexity of the theory comes from these singular, in some cases, infinite distance limits, which to me, at least for the type of examples that we have in string constructions, is a little bit surprising. I don't know if it's because of like the value, because usually around infinite distance limits, our functions and expressions are like simpler, and you would expect that it's in the bulk where you have more complicated expressions. So is there any intuition on why for you it's this infinite distance or like the specific singular points that matter the most?
Well, in general, and this is something that has puzzled us a little bit during this whole process. But the thing that is more likely to break finiteness, it's infinite distance limits. So these are like the most concerning. Then you're also So whenever you have
It's
something
because
that
you
is
would have like more fields there, for example.
Yes, exactly.
Or
So
like
you have
okay.
So whenever you have something that is compact, time theorems become very simple. So it's infinite distance points which provide most of the problems. And regarding the bulk, we do expect the bulk to be much more challenging, but from our perspective, we are putting a cutoff. So in principle, all these problematic or more difficult things are maybe being left out of the description of they are not contributing to the complexity, and the things that could contribute are for example, the light states of the tower, or things that are modifying the reach of our effective field theory. Yeah.
Okay, I see. Thanks.
Okay, if there's no further questions, then we can thank David again, and then Marco can start setting up.